So we want to show the tetrahedron CMM verification. Here we have a CMM and here we have a tetrahedron. I will unpack it. This is our tetrahedron for today. And this fits nicely on the machine. I will show how quick the setup is done. So we need to fix it to some prepared reference fixtures, which are nothing else but 3 screws. If you have a ball head for these screws, it's better, but it's not necessary. Lock the screws in the thread in the table of the CMM. And now I put magnetic rod on the feet of the tetrahedron. And the tetrahedron is fixed in its place where it's always made. So now let's start to measure. The program is always the same, and as the tetrahedron is in the place where it always is measured, I don't need to make an alignment. I say existing alignment and run the program. This is not just the fastest machine now. We put it always very slow due to safety reasons. It is not a machine where we make mass measurements, but relatively high accuracy measurements. So, while the tetrahedron is being measured, I try to explain a little bit. So the tetrahedron method is a method which makes use of a 3D object. We all know that when we check a machine with 1D objects, we have to measure a lot of lines. A tetrahedron is a 3D object, so actually we need to measure it only in one position, and we get spatial information about the accuracy of the CMM in space. As you see, we have 4 balls, and between the 4 balls are 6 rods. And 6 distances can be defined between those 4 balls. Actually, the ball centers. And all those distances are somehow space diagonals, are diagonals on the machine. We measure each sphere with about 7-8 points. That is enough. And then we calculate in the software the direct spatial distances between the 4 spheres, 6 distances. So this takes about 4 minutes, the measurement on this machine, which is set to be very slow. On a fast machine, it could be done in 2 minutes, let's say, 2.5 minutes. We have to be careful when we assemble this, that the screws are locked, and let's try to shake the tetrahedron when we mount it, whether there is not some of the elements loose. That's the only concern we have. The balls had been cleaned before, and the box is clean, where the tetrahedron is stowed away, so we normally don't need to care about the dirt. We will see that dirt anyhow from the form errors of the sphere measurement. So these are the last points, and things are done. The tetrahedron has been measured. I can put it away actually, and now I go and evaluate. Evaluation consists simply in taking the measures from the machine to the computer with the evaluation program. So what do we have prepared here? We have prepared 6 distances. I transfer those to the computer. As these are only 6 distances, it is not absolutely unnecessary to make any automatic transfer. So I see here we have 603.7969. 603.7969. Well, to the decimal it is the same thing as before. So I don't need to change anything. Let's go to the next distance. 603.8953. 603.8953. In fact, it's identical again. I have to go to the hundredth of a micron. 603, 62144. 62144. 3 decimals change of a micron. Next one. 603, 5041. 5041. I have a decimal of a micron change since last time. Actually, I'm running a repetibility check on this machine now. 603.4972. 4972 to the 10th of a micron. And last one. 603.1717. 1716 it was, so we have a decimal change. Now let's try to get closer to the computer. I'm not sure whether this works well. I have to take the camera off the tripod and see what I can make visible there. So I have put in those values here, and now I press the button, evaluate, and store in the history file. And in the history file all the measurements before are stored, among others those length changes, and here we see the length change has been virtually nothing, a decimal of a micron for that length which came out worst. We have here several graphs. For example, here we have all the different lengths, all the 6 lengths, in comparison to the maximum allowed errors. And that over time. So if I press several times here in the input on that macro, then the evaluation is done again, but now with the same values, and I get a new entry. You see there are now 6 entries. If I press again store results, it evaluates again the same results in this case, because I didn't enter anything new, and you see there are 7 now. So we have these 6 lengths over time, multiple times. For those who don't want to bother with all the 6 lengths, here is a diagram which shows only the worst length. And so this is a nice X-bar chart over time. So now you can imagine the tetrahedron can be put away in half a minute in its box, and then things are done. Let's do it. Unlock the magnetic rods. Open the box. Put the tetrahedron in. Put the rods in. Close the box. And that was it.